Everyone, welcome to the 7th lecture of particle physics. We are starting with the flavor symmetries. Okay, so in case of a nucleus, mass of proton and mass of neutron are approximately very same. So Heisenberg regarded them as two states of a single particle, and he named them collectively nucleus. I mean, we can call any one of them as nucleus. He said that a strong force experienced by proton and neutrons are identical. Okay, that is what he said. Now we write nucleon as two components considering n is equals to alpha and beta, where n is just a nucleon and it can be divided into two parts, proton and neutron. Actually, this is just a notation. Do not consider this as a matrix or like that. Okay, so from this statement that the mass of proton and neutron are very similar, we go into a fact that that we introduce an isospin. Now isospin is very similar to spin S. Spin is actually very similar to spin, but there is a difference that spin has some component in x, y and z direction in ordinary space, but isospin has an imaginary space which is called isospin space, and it has imaginary three components in its imaginary space, and that is I1, I2 and I3. So if we have to represent proton and neutron in different form, we use the isospin form, and this is how we represent, and this is how we represent. N contains minus half and P contains plus half. This is called isospin up, and this is called isospin down. For minus half, isospin up. For plus half. Now these are still just a notation. We don't say anything sure for now. Now physics comes in Heisenberg's proposition that a strong interaction is invariant under rotation in isospin space. That means he said that regardless of proton and neutron, the strong force is applying on both of them similarly. Now we notice here that the isospin of proton and neutron are different. So if the strong force is same in case of proton and neutron, then strong force must be invariant of the spin. Okay, so in ordinary space, electromagnetic force is independent of rotation, and we call it internal symmetry. Obviously, no matter how we rotate a particular charge, the electromagnetic force is going to be the same on that particle. So we call it as the internal property of that matter, or call it the internal symmetry thing. But for a particle, now we are looking for a particle. In case of a particle, if you rotate a particle by 180 degree, then you can see that if we rotate a proton by 180 degree, then it will convert into a neutron. That is, the isospin number will change by 1. Okay, so a rotation through 180 degree about axis number 1 in spin space converts proton into neutrons, and vice versa. So we can introduce here the Noether's theorem. We can say that isospin is conserved in all strong interaction. Now in the language of group theory, Heisenberg asserted that the strong interaction are invariant under an internal symmetry group. Okay, this one is very important. We know that this is a symmetry group, and kind of a rotational symmetry group also. It can also be written as SO3. So it is a kind of a rotational symmetry group, and it must be invariant. Okay, it must be invariant, and the nucleus and nucleons belong to the 2D representation. Okay, it belongs to the 2D representation only in the case of isospin is equals to half. If isospin is to be 1, then it belongs to the 3D representation. If isospin is 3 by 2, then it belongs to the 4D representation, like so on. Now those were the protons and neutrons. Now we are looking at the pions. Pions has an isospin of 1, and it can be subdivided into its third component of isospin, that is 1, 0 and minus 1. Similarly for lambda, it is only 0, 0. In case of delta, we have delta plus plus, which belongs to 3 by 2, and the I3 component is 3 by 2. For del plus I3 component is half. Now del naught I3 component is minus half. For del minus I3 component is minus 3 by 2. Number of particles in the multiplate is actually 2i plus 1. So from here we get the multiplicity. I mean the same kind of particle is actually, you can say, is multiplicity. Okay, So the same kind of particle could be involved in multiplicity, and the number of multiplicity can be derived from a single particle's isospin. Okay, now it is further modified by Gellmann Nishijima formula. Q is equals to I3 plus half B plus S, where B is the baryon number, S is the strangeness, and I3 is the third component of isospin, Q is the charge. This equation is actually empirical observation only. It is not some derivation, it is just an empirical observation. Now isospin can also be seen in up and down quark, with up quark having I3 is equals to plus half and down quark having I3 is equals to minus half. Now in all other quarks, or you can say flavors, isospin is always 0. So from the rule of addition of angular momenta, if we combine two nucleon, we get total isospin 1 or 0. So in case of nucleon, we have a neutron with half, neutron with minus half and proton with half isospin. Okay, so the case is that both have these are the third component of isospin for neutron and proton. The isospin is having half and half for both of them. Okay, so what total isospin can we have if we form a neutron, nucleus, using only these two particles? It can obviously make a nucleus with isospin of 1 or isospin of 0. Okay, so for case of proton and proton, both have third component as plus half and plus half, so we have I is equals to 1 and I3 is equals to 1. In case of neutron, both having third component as minus half, we have minus half as third component. Now in case of proton and neutron plus neutron and proton, this is kind of if you remember, this is a symmetric representation of wave function. So in case of symmetry, symmetric case, P and N are merged together, and we know that the I3 component of P is plus half and neutron is minus half, so both of them combine to give I3 is equals to 0. So it can be written as that, and it is root 2 is actually the normalized value, root under 1 plus root under 1. Now there is another component which corresponds to isospin is equals to 0, and that is 0 comma 0. This is actually called the asymmetric isosinglet. This is called the asymmetric isosinglet. Okay, so in here, since asymmetric is present, so we have to put a negative sign here. Now we have to find that where does this antisymmetric or asymmetric isosinglet exist. Okay, well, experimentally, neutron and proton form a single bound state, and that is called Deutron. But obviously there is no bound state of 2 proton and 2 neutron only. Thus, Deutron must be the isosinglet. Or there is another proof, that is the total wave function is actually the multiplication of space part, spin part and isospin part. So in case of a Deutron, its spin is 1, its space parity is actually minus 1 to the power L, and L is the angular momenta. And in case of Deutron, angular momenta can have only two values, 0 or 2. When we put 0 or 2 in here, we find that the phi is equals to 1, that is the space part is also 1. So wave function should totally be equals to antisymmetric. Now in case of 1 and 1, this is looking kind of symmetric. So to make it antisymmetric, we use the isospin of antisymmetric part. Okay, therefore that antisymmetric isosinglet is actually of Deutron. Now evidently there is a strong attraction in I is equals to 0 channel, but not in the I is equals to 1 channel. When you will read Deutron, you will understand why. Okay, well, the potential described in interaction between two nucleons containing a term I1 dot I2, which takes the value 1 by 4 for triplet and minus 3 by 4 for singlet state. Obviously, now let me remind you of something, that in case of a cell model, you may have stumbled upon this VR L1 dot L2 type potential. Okay, so here L1 dot L2 potential is dependent on L1 dot L2. Similarly kind of potential we can see in here too, where the potential is dependent on isospin of both the particles I1 and I2. Now if you remember that in case of if we have normal spin half, then s1 dot h2 for two particles is equals to this formula. Okay, and this formula is actually equals to s square minus s1 square minus h2 square by 2. This is this. Okay, and when we put s is equals to 0, that is for singlet state, we get minus 3 by 4 h bar square, and in case of triplet state, s is equals to 1, we get 1 by 4 h bar square. Okay, now it is same as here I1 dot I2, where we get 1 by 4 for triplet and minus 3 by 4 for singlet state. But remember that there is no h bar in both of the cases. There is no h bar because isospin space is kind of a imaginary thing, and it is h bar is not included in here.